Hello and good afternoon. Thanks for joining. My presentation is about NOEL-V, which is our RISC-V IP core. It's actually a set of IP cores implementing 32 and 64-bit RISC-V that is tailored for different use cases or application profiles, if you will. So at CAES, we consider ourselves a world leader in embedded computer systems for harsh environments. Our own parts are mostly, with parts I mean components, are mostly targeted to the space application domain. However, since we not only use our IP for our own parts, but also license the IP, it is essentially open for anyone to use, and it is being used also in industrial or commercial applications. So we not only provide IP or components, we also provide an entire ecosystem that includes debuggers and compiler tool chains. Traditionally, we have made a lot of processor models in the Spark architecture, which still is dominant in spaceflight, but now we're running a dual architecture portfolio with RISC-V and Spark. So the RISC-V, NOEL-V processors are part of a larger IP core library. Again, these IPs that are some of those which are mentioned here are used in our own projects as well as projects that our customers do. And it has always been also released under GPL. So most of the IP that is part of our library is as well available for download as GPL. So in terms of software, we provide a number of different compiler tool chains and operating systems. Most of those are available as our own releases that work out of the box for all our processor models. We support the GCC as well as the LLVM compiler for a number of those. We also work with a number of partners. For instance, Fentis is doing a Hypervisor Extratum that we are demoing here as well at our booth, which is just over here. Cisco with Pike OS is another hypervisor solution. Wind River as the provider of the VxWorks operating system, we are also working very close with. We're providing our own bootloaders. Those are mostly targeted again for spaceflight. This is bootloader software. But in terms of debug tools, we not only provide our own solution, which is called Gearman, as a low-level assembly-level debugger, but we also cooperate with Ashling, who are here present as well, for their support in the risk-free IDE of our NOEL-V processors. So our licensing model for our IP is threefold, I should say, or actually fourfold. There is always a open source version of both the RISC-V as well as earlier processor generations that has been released. That contains most of the IP that is available. It is released under GPL, so it is not always or hardly suitable for a commercial product. For that purpose, we have commercial license models available. And then on top of that, we also have a fault-tolerant release that includes all the previously mentioned releases, but also adds fault tolerance to all of the IP that is part of the respective release. So just as an example, what we use our IP ourselves for, here's a number of components that we have developed over the years. Some of them are still under development. So most of the IP that we provide is at least silicon proven by our own components. And I think this makes it a little bit a differentiator because we not only develop IP for licensing, but also for integrating them in our own components. Now look a little bit at the NOEL-V processor core. It's it's 32 and 40 64-bit profiles that we provide. It supports the AHB bus, but also the AXI bus. Here you see some performance figures that we achieved. If you're interested, of course, performance figure is always dependent on a number of things. We've tried to make that a little bit clearer by specifying some conditions where they were achieved. If you're interested in those, please come and talk to me. Quick overview of the different RISC-V extensions that we have implemented. Again, these are processor subsystems that are ready-made as base configurations for different application and performance profiles. And then on top of that, those are also still configurable in the VHDL code, for instance, in terms of cache size or other very important implementation specifics. So here we have a little bit more detail about the different extensions that have been implemented that can be chosen during implementation on FPGA or ASIC. As part of processor peripherals, we have implemented a level 2 cache that today we always implement in silicon on higher performance devices. We have implemented the RISC-V debug module, which makes it very compatible to the entire ecosystem of debuggers, and Ashling that I've mentioned earlier is only the first instance of a validation with the RISC-V debug module as an underlying physical access. There's also a number of other notable IP that we have developed at the same time, which is some DDR and DDR3 SDRAM controller, also a NAND flash controller that supports ONFI 4.0, I think is worth mentioning. In terms of availability, there is always the GPL package that can be downloaded without any registration or anything from our website. It is not only a source package with all the source code, but also there is a package of bit streams for particular standard FPGA evaluation boards. So it is very, very easy to evaluate either for hardware developers where the RTL is available in open source, or also for software developers that want just to use a ready-made platform and download a bit file on their card and can start prototyping or evaluating, benchmarking their software for RISC-V, for NOEL-V on this particular board. Coming from the background of spaceflight, fault tolerance is one of our differentiators. Fault tolerance essentially means implementing EDAC on all on-chip memories. But that's not necessarily enough. Of course, many processors do that today. However, what is more important as well is that the entire system is constructed in a way that it can react and respond to potential faults in an immediate manner. Other concepts are scrubbers, where SRAM primitives such as caches are actually being continuously read and rewritten in a loop in the background to avoid the buildup of correctable single-bit errors. In terms of future developments, we have a number of additional support for additional extensions and features that is planned. For instance, pending is a release that adds trace support and also bit manipulation and cache management extensions. Further down the road, We want to implement more DSP-like single instruction, multiple data extensions, as well as the packed and vector extension as two examples. We have demonstrated already a while back the NOEL-V RISC-V core on a 28 nanometer red hard demonstrator together with ST Microelectronics. So that was when the RISC-V, when the NOEL-V processor first gained silicon, was silicon proven, and it has performed to our expectations. We have done radiation tests with that part, so this is actually a space-grade IP. One of the more advanced developments that we're currently undertaking is a 16-core RISC-V processor with islands of 4 processors each. Each of them have the level 2 cache integrated with a third level of level 3 cache wrapped around or integrating in a high-speed interconnect matrix that provides also quality of service. So this is really an advanced multi-chip, multi-core system on a chip that we will implement in an advanced technology node. We have also implemented the Hypervisor extension. There is a number of Hypervisor software that can be run on the NOEL-V. We have particularly partnered with Fentis to demonstrate Hypervisor, and it's actually, we have a demonstration running here at the booth with the Fentis Hypervisor that makes use of the Hypervisor extension implemented in the IP. So as a summary, NOEL-V is a configurable RISC-V IP targeting a broad range of applications. I think we've seen that between very small single core and 32-bit and 64-bit multi-core implementations with superscalar pipelines can be implemented. It can be implemented as well with fault-tolerant features. GLib FT IP cores allow the correct operation in the presence of correctable errors. So, of course, fault tolerance has been implemented in many processes, in many IPs. I think it's a standard in the automotive as well. However, not always the systems have the ability to actually react on the fault when it occurs, rather than continuing until a non-correctable fault actually shows in the application. The NOEL-V is silicon proven on ST's 28 nanometer platform. We have in the pipeline several multi-core advanced systems on a chip that are being developed currently. Again, we are showing the Hypervisor extension with the Fentis Hypervisor software. And finally, the NOEL-V processor and the GLib are not only licensed commercially, but also available under a GPL license directly from our website. And I think that's really what is important for many here, is that you have the ability to directly evaluate and test and try on every software and hardware level that you can think of. Thank you very much. That's what I wanted to show you today. And please let me know if you have any questions.